Hello, today we will discuss about bioelectrodes or biopotential electrodes. We know that in man instrumentation system, we have to pick up the signals or action potentials that has been generated at different organs, or we call those signals as biopotentials. So, these biopotentials has to be captured. Before going to the different types of electrodes, we must know some about these terminologies, which will help us to understand the functionality of different types of bioelectrodes or simply electrodes. So, in electrolysis process, we know that there is some electrolyte. This electrolyte is a substance which contains free ions, and we have electrodes. These electrodes are basically metallic conductors and which provides physical interface between your electrical circuit and this electrolyte. And similarly, we have cations. Cations means positive charge ions, and these cations, they are moving towards the negative cathode, because cathode is negative and these ions are positive, they are moving towards the cathode. Similarly, we have anions. These anions are negative charge ions and they move towards the anode, which is positive terminals. This process involves two reactions like process of oxidation. This process of oxidation means it is the removal of electrons, at anode, and your next one is reduction. This process is the addition of electrons which occurs at cathode. So these are some processes which are actually going on during the process of capturing these signals or biopotential signals. So we will see how they are helpful in pick upping these signals. Basically, this bioelectric phenomenon, they are associated with distribution of ions or charged molecules in a biological structure or organ, and which as a result of biochemical reactions going on inside and outside the intracellular and extracellular fluid. We know that there is a charge separation, or the concentration of charges are different at different instants of time across this semi-permeable membrane of the cell. So this creates action potential, and these bioelectric electrodes are fundamental interface for acquiring and studying biopotential signals. We know that these biochemical reactions, they produces different ionic exchanges, and those ionic exchanges must be converted to an equivalent electronic conduction, and this process is known as a transduction. Through the transduction function which is carried out by the electrodes, we can capture those biopotentials. Bioelectric events have to be picked up from the surface of the body before they can put to the amplifier for amplification process or further execution. Basically, we can see here we can see the properties of bioelectrodes. They have some interesting property, or we have to choose accordingly. so that we can capture very sensitively. So, they should be good conductor. First thing, the bioelectrodes must be good conductor. They must have low impedance so that very low amplitude signal can be captured. They should not be polarized. They should establish a good contact with the body so that during any motion there will no noise created or no artifact. Similarly, potential generated at the metal electrolyte surface should be low and they should be chemically inert. These are the characteristic of a bioelectrode. So, we will see what are there are some examples here I have given for the different types of biopotentials or bioelectric signals. We can have electrocardiogram, we have electroencephalogram. This electrocardiogram is related to heart or action potential generated at heart. Similarly, electroencephalogram records the action potentials of these brain waves. Similarly, we have electromyograph, the action potential generated of muscles. Electroretinograph, here it is electrooculograph, it is related to eye. So, these biopotentials or these bioelectric signals, they has been captured through different electrodes. For example, this ECG is captured in using some surface electrodes. EEG is captured or electroencephalogram can be captured through some scalp electrodes. We will see what these different electrodes, they are also categorized into different class, they are categorized to different types. So, we will see one by one what are the different types of electrodes. Now, basically we have two different types of electrodes, one is surface electrode, another one is deep seated electrode, or we can say these electrodes are just put, or we can place these electrodes under the skin or epidermis. So, these are invasive in nature and surface electrodes, they are non-invasive in nature. So, you can mark here different surface electrodes are metal plate electrodes, we have suction cup electrodes, we have adhesive electrodes, floating electrodes, multi-point electrodes, flexible electrodes, and similarly this deep seated electrodes, they are of two types, one is microelectrode, another one is needle electrodes. These needle electrodes, they are capable of collecting the biopotential even if from cellular level. So, now we mark this microelectrode, they are of two types, one is metal microelectrode, another one is glass microelectrode. So, these electrodes we will see in the later slides. Now, whenever any electrode system, electrolyte system we come across, there is an interface developed. So, this is called metal electrolyte interface. Now, this metal electrolyte interface you can mark when one metal electrode is placed inside one electrolytic solution, what will happen at this interface, this is the interface which has been zoomed here. So, here you can mark the interface of metallic ions in a solution with their associate metal results as an electrical potential, that is called electrode potential. What happens? Actually, at this interface which has been shown here, the electrode discharges ions. This electrode, it discharges ions into the solution, like this M plus ion will be discharged. When this M plus ion discharged, or this cations are discharged into the solution and leaving behind these electrons inside this electrode metal. So, this layer you can mark here, it is negative electrons, and in this part it is a positive metal or positive, or it is your cations. Now this will create, we can consider this as a double layer. One layer is negative, one layer is positive across this membrane or across this interface. It is just similar to one capacitor. Two metal plates across one membrane, we just consider this, it is just similar to one capacitor. So this ion electrolyte, here some of the inside this solution or electrolytic solution, we know that negative ions are also there. They are attracted towards this double layer for recombination or for the combination process. Means this positive ion, that is a cation, and this negative anion, they start combining at this interface. So what happens due to this charge separation here, negative and positive, and this accumulation of the charges, this create a potential difference at this electrode and inside the electrolyte. This arrangement of the ion interface is called a double layer. This potential is result due to the difference in the diffusion rate of the ions into and out of the metal. So equilibrium is produced when by the formation of the layer charge at the interface. That means when the number of cation and anion which is exchanged is equal in number in both directions, then we can have a equilibrium. This charge is really a double layer, with the layer nearest to the metal being one polarity and layer next to the solution being opposite polarity, that we have already discussed. So the non-metallic metals such as hydrogen also have electrode potential which interfaced with their associated ion in the solution. The normal hydrogen electrode was chosen as the reference standard, or we call it as a standard hydrogen electrode, SHE. And with respect to this SHE value, we are measuring all other metal electrodes, potential of the all other metal electrodes. So this electrode potential of hydrogen is considered as 0. With respect to this voltage, other metal electrode potential has been calculated. This will govern by one equation. This potential developed across one metallic electrode and the electrolyte solution is developed or is considered through one equation. This double layer can be considered as simple parallel plate capacitor, and the metal electrolyte interface appears to consist of a voltage source, a capacitor, and a resistance due to the reaction. This voltage is called half cell potential, because, or we can say electrode potential. It is either we can call it as a half cell potential, or it is also known as initial electrode potential. All electrode potential as measured with respect to that hydrogen, standard hydrogen electrode. Okay. So now this equation, now we can see this Nernst equation, that will give you what is the electrode potential generated by an electrochemical cell for a given set of concentration and activities. So in this case you mark, if as we have seen here, one electrode is put inside one electric solution, this interface which we have considered as a double layer. Now considering this double layer, we will see what will happen across this semi-permeable membrane. When the membrane separates liquid solution with different concentrations of that same ion, what will happen? An equation relating to the potential across the membrane of the two concentrations of ion is called Nernst equation. So you mark this electrode potential, it depends on this gas constant, the absolute temperature, RT by N. N is the number of electron transferred during the electrochemical reaction. F, as we know that it is your Faraday constant, 96,485 coulomb per mole, and here it is the ln of C1F1 by C2F2. C1 and C2 are the concentration of chemical species involved in the redox reaction, because we know that at the electrode we have we have oxidation process as well as reduction process going on, and F1 and F2, they are the activity coefficient of the respective chemical species. So, using this Nernst equation we can calculate what is the electrode potential generated during using that electrochemical cell. So, now as we see there, as we have seen that here you have electrode and electrolyte. This is your double layer or the interface of the electrode electrolyte, and you know that these electrons are, this is your metal side or metal electrode side, this is your electrolyte side. These electrons are moving away in this direction and these cations are moving in this direction into the electrolyte, so that there will be a combination process inside this electrolyte to produce a mass. So, an electrode potential is developed across the interface, which is proportional to the exchange of ions. How many number of these cations, anions are exchanged across this double layer, and this double layer you mark, if this is your electrode side, here this double layer is considered as one capacitance. This will give you this chemical reaction resistance, and here it is the resistance which is given, and the potential developed, it is your initial electrode potential, and it is connected to your body electrolytes or tissue. The double layer of change at the interface act as a capacitor. The ionic difference are source of half cell potential, as we have discussed. The electron moving in an opposite direction of the current, that is your C plus or cation moving the same direction of current, and anions moving in the opposite direction of the current. So, in the oxidation process in the metal, you can mark here metal electrode, this A will now become An plus, and it is leaving behind the electrons, means it is generating the cations, and here it has some electrons, these are the electrons. And the reduction process, what happens, they will add up, this is the addition of electron to form the neutral atom. So, you can see this half cell potentials of different electrodes can be seen here. If it is a aluminum, then 3 electrons are generated, and it is giving you minus 1.706 as is half cell potential. All these electrode potentials are measured with respect to this hydrogen potential, half cell potential. It is known as your standard hydrogen electrode potential. Similarly, you have zinc, here you have your copper, then Ag plus Cl, it will give you plus 223, silver is giving you plus 799. So, different potential, initial potentials or electrode potential has been shown. The electrode is made up of some atoms of the same material as the cation, and of this material, let us say if it is same material, means if you have considering Ag, the cation will be equals to Ag plus, and this material is the electrode at the interface can be oxidized to form a cation Ag plus plus E minus. So, this is a process of oxidation, and one or more free electrons. The cation is discharged into the electrolyte. So, this AgCl will be discharged into the electrolyte, the electrons remaining as charge carrier in the electrodes. As we have seen here, these electrons are remain inside the electrode as charge carrier, and these cations will be released into the electrolyte. The electron remains. So, in this case an anion coming to the electrode, now what will happen, this Ag plus will released into this electrolyte, now try to combine with, let us say inside the cell we have some ions like Cl minus, these are the anions. So, they will move towards this Ag plus and try to combine with it. So, in this case an anion coming to the electrode electrolyte interface can be oxidized into a neutral atom, giving off one or more free electrons. They will attach or they will combine to give rise to some free electrons like Ag plus Cl. So, it will give you AgCl compound and some electrons. Now, for example, an electrode consisting of a piece of zinc with an attached wire and another electrode consisting of piece of silver coated with a layer of silver chloride and attached wire placed in the zinc chloride solution. So, activities of zinc and chlorine ions, they are approximately unit, means 1. So, activity as in the Nernst equation we have seen, this F1 and F2 are 1 and 1. So, to form an electrochemical, what is the chemical cell that is maintained at a temperature 25 degree? So, first question is, what is chemical reaction might be expected to see at these electrodes, because we have 2 electrodes and we know that what are the half cell potential for Ag electrode, for zinc electrode. So, 2 electrodes we have, one is zinc, another one is Ag. So, we can see from the table what is the half cell potentials of this zinc and your AgCl, this one. So, now because AgCl we have taken, so now you can mark at the zinc electrode is anode. So, oxidation takes place. When oxidation takes place, it is your zinc 2 plus aqueous solution plus 2 electrons are removed and zinc is oxidized, losing 2 electrons. And at the AgCl electrode, at this electrode it is your cathode. At this cathode what will happen, we create one AgCl plus, this is released. So, we have Ag and Cl, Ag will be solid Ag and Cl minus will be aqueous solution. So, silver chloride is reduced by addition of this electron, gaining electron to produce Ag and Cl minus. So, this process is happening, one is at anode, another one is at cathode. So, the cell voltage is given by the difference of the standard reduction potential. So, what is the cell voltage developed, that can be taken from this equation. One is the cathode potential minus the anode potential. So, AgCl potential is plus, approximately it is plus 22 volt, as we have seen from the table, it is plus 223 volt, and zinc is minus 76 volt. So, here it is zinc is minus 0.763 volt. Okay. So, this can be calculated by just subtracting from E cathode minus E anode. So, we are getting 0.98 as the potential developed across this due to this electrochemical reaction. And this potential is known as offset potential. The difference in the half cell potentials that exist between these 2 electrodes is known as offset potentials. Now, coming to the different types of electrode in terms of polarizability. In perfectly polarizable electrodes, we have perfectly non-polarizable electrodes. This is a non-polarizable. So, perfectly polarizable electrodes means those are the electrode no actual charge crosses the electrode electrolyte interface when a current is applied. there has to be current across the interface and the electrode behaves as through it via a capacitor. But in non-polarized electrodes, they are perfectly reversible, means once we draw those external sources, then it will again repolarize. So, these non-polarizable electrodes are those in which current passes freely across the electrode electrolyte interface, requiring no energy to make the transition. Thus, for perfectly non-polarizable electrodes, there are no overpotential. Electrode interface impedance is represented as a resistor. So, we can see here non-polarizable electrodes, they have no overpotentials. Now, when we place the electrode on a surface of the skin or surface of the body, then it will, the interface is just looking like this. We have the tissue, then over that tissue we have the interface, we have to place some electrolytic jelly, and there is an interface in between this tissue and the electrolytic jelly. We call that electrolyte skin interface. Then between this electrolyte jelly and to this instrument, we have one metal electrode. So, this is another interface. This is your electrolyte electrode interface. So, these two, we know that if we have two different electrodes, then those two different electrodes can be modeled as these two different electrodes. Okay. So, here you mark, it is our body tissue and fluid, which can be modeled as some with some capacitance and resistance, and we call this bioimpedance or skin impedance. This model is known as skin electrode impedance or contact impedance. Now, this is the equivalent circuit for the electrode 1, this is your circuit for the electrode 2. Now, the different types of electrodes, as we have already discussed, metal plate electrodes. In the metal plate electrode, you can see there is a contact surface, then we have some lead wire terminals and then the rubber support belt. So, this will be placed over the surface of the body, and we are placing some electrolyte here when we place them on the surface. Then they are clinically used in ECG, but they are more prone to your motion artifacts. So, that is why we require a stability for more firm attachment. We can go for suction electrodes. These suction electrodes are just like this. So, there is no adhesive, but they are very firmly attached to the body due to the suction pump like action. Similarly, we have floating electrodes. There is no direct contact in the body, and the metal electrode separated by gel layer, and it will reduce the motion artifact. This type of floating electrodes, they are used in ECG, EMG, EEG all, and one of the example is your Ag-AgCl. This Ag-AgCl electrode types are also used as a floating electrodes. So, this is the diagram for one floating electrode. We have different skin here, adhesive, then flip, all these arrangements are for these floating electrodes. Now, flexible electrodes are made of flexible materials. Here you can see different flexible materials we have used in the wearable sensors. And disposable pre-gel electrodes, adhesive with pre-applied gels. Gels means these are the electrolytic gels. They are convenient for clinical use and they can be disposable once it has been used. Then dry electrodes, there is no need for gels. They are actually use the concept of capacitive coupling or conductive polymers. So here you have conductive fabric membranes, stainless steel, all these are some of the pictures of these different types of electrodes. Now the final one is your Ag-AgCl electrode, which is very useful because the advantage of using this Ag is they are quite stable for biological application, and they are easy to fabricate in lab. So in this diagram you can mark here one Ag wire is there, a silver wire which has been coated with some silver chloride AgCl, and it has been put inside one solution which has more concentration of chlorine ions KCl. Now we will see how it operates. The Ag-AgCl electrode has the characteristic of a perfectly non-polarizable electrode, as we have discussed. As we have already discussed, the non-polarizable electrode, they does not have over potential. So it is easy to fabricate in lab and is widely used in biological and electrochemical applications. So this silver metal base, it has been an insulated lead wire which has been coated with an ionic compound, that is your AgCl, which is slightly soluble in water. So that is why it is stable. The electrode is immersed inside an electrolyte, which is principal ion is Cl minus, and basically we are using KCl there. Okay, that will become K plus and Cl minus. Two reactions are occurring at the place of electrode surface. What is that? First one is oxidation of silver atom. We know that this Ag will become, in the metal that we use this metal base, it become Ag plus and one electron will be released. Similarly, this Ag plus will attached or it will combine with the Cl minus which is present surrounding that, and it will create the AgCl base. And biological fluid, the concentration of Cl ions is relatively high, as we already know, giving it is an activity just less than unity. The solubility product, that is Ks, solubility product is like the concentrations you have here. What is that value? Ag plus and Cl minus. What is the value? We multiply that, it will give you the solubility product. The AgCl approximately 10 to the minus 10. This means when an AgCl electrode is in contact with biological fluid, the ionic activity remains stable, it is very less. So we know that half cell potential can be calculated using this formula. Previously we have seen that in Nernst equation. Okay. So now in this case we have to calculate what is that concentration. It is Ag plus, and we know that solubility product from here Ks equals to Ag plus into ACl minus. So this again we can put here in place of Ag plus, we can put here Ks by ACl minus. So now the equation we are getting for this biological or this potential developed, that is your half cell potential given here, or previously that electrode potential, then this equation it is RT ln Ks, and this division is becoming minus here. So minus RT by NF ln ACl. This half cell potential of this electrode remain quite stable when placed in an electrolyte containing Cl as the principal ion. So in this manner, if you know these concentrations, then we can calculate what is the potential developed. So these are the schematic representation of Ag-AgCl electrode, and here you have this K plus and Cl minus, and using this electrode we can also measure, this can be measured as reference, and we can measure other potentials or biopotentials. Now coming to the microelectrodes, which are invasive in nature or which are deep seated electrodes. we have two types, metal microelectrode and glass microelectrode or micropipettes. In metal microelectrodes, you can see here the electrolytic jelly etching the tip of the fine tungsten to the desired size of the dimension. And here the micropipette types microelectrode is a glass, it is not a metal. Okay. When the wire is coated to the tip with any type of insulating material, but in the micropipette it is filled with an electrolyte which should be compatible with the cellular fluid. The metal ion interface takes place where the metal tip contacts the electrolyte, and the main features of the metal electrodes are very good signal that is to noise ratio SNR. Similarly, strong enough to penetrate the tissue, high compatibility because we are using metal. In this case, a micropipette is a small and extremely fine pointed pipette used to making micro injections. So, now this is one example. This figure is giving you the metallic electrode and it is your micropipette electrode. Both can able to extract the potential across this cell membrane. So, this is a cell membrane, this is the metallic tip through which we can collecting the signal and the difference with respect to the reference electrode has been captured. Here also this glass pipette, it is your glass, this is made up of glass, and here you have the electrolytic gel and this is your electrode, metal electrode. So, this tip we can penetrate inside the intracellular fluid and there is the due to this ionic reactions we can capture this potential, and those potential is taken across with respect to some reference electrode and that has been put for amplification. The last one is your needle electrode. This is very small subdermal needle electrodes under the dermis of the skin. It can be put so that it will reduce the skin impedance and also reduce the noise or artifact. It is also basically used in electromyogram from muscle biopotential recording from of the muscles. Sometimes it is used for electroencephalogram. They are inserted parallel to the skin surface for stable and minimal invasive signal acquisition. So, this is all about electrodes. In the latter stage we will see different topics. Thank you.